Hello, Dr. J here. Today we're going to talk about voltage, current, and its relationship with power. First of all, voltage. We saw in earlier videos that voltage is like an electrical pump to provide electrical pressure in moving electrons found in a circuit. And we also saw in earlier videos that voltage supplies the energy to move those electrons. We also know that work is equal to force times distance, as discussed in earlier videos, and we know that the unit of work is joules. However, the unit of voltage is the well-known volt. So how is volt and joules related? So we'll take a closer look at this on the next slide. First, we have 1 coulomb. To move that electron, it requires work. Okay, and say we move 1 meter. Hence, we define volt as the amount of energy to move 1 coulomb of charge 1 meter. Hence, that's the relationship between volt and work, where work has units of joules. Now, how does it relate to power? Well, power has units of joules per second or watts. Current, as we saw in earlier videos, has a unit of ampere, which we further can define as coulombs per second. Voltage, we just saw, has units of joules per coulomb, which is the volt. We have a relationship that is very important because we got to make sure that we don't exceed the power requirements of a device such as a light bulb, so that the product of the amount of current going through the light bulb and the voltage across the light bulb, those two cannot exceed the power requirements associated with the light bulb. Alright, so let's take a look at this relationship. P equals to IV. Well, let's do units. You do that a lot in physics, is just to look at the units to see everything works out. So we know that power on the left side is joules per second, and that the right side we have current as coulombs per second and voltage as joules per coulomb. But here we see that the coulombs cancel out, meaning that the left side units and the right side units match. Now, in order to help you remember this formula, it may sound corny, but we have a mnemonic that I used and give it to the students, and it's called poison ivy. Another one is called VIP. In other words, VI is equal to P. So hopefully those two mnemonics will help you remember this important formula such that we do not exceed the power requirements of a particular device in terms of current and voltage. As a simple illustration of this formula P equals IV, let's look at this example. Let's say we have a device that cannot exceed 100 watts of power. The maximum voltage across this device is 200 volts. What is the maximum current for this device? So if we take this formula and divide V on both sides, we get P divided by V as one side of the equation. The V's cancel out and we're left with I as shown here. Substituting, we have 100 watts in the numerator, 200 volts in the denominator, and that gives us a value of 0.5 amps. So for this device, we cannot exceed 0.5 amps if the voltage across the device is 200 volts.